Thanks very much for having me. It's a pleasure to be here and present in this very compact way. I hope that people on Zoom hear me well. So yeah, so I chose this clickbait title, and I will later explain why is it like that. So as Andre mentioned, my name is Miroslav Macko. I come from Czech Technical University in Prague, and I'm also active in SuperNEMO collaboration. And also to get a bit more precise introduction, before I come to the agenda, I decided to tell a tiny bit about my path, because it also reflects the activities we do with my group at CTU. So I originally started my bachelor and master degree at Comenius University in Bratislava. So this was standard general physics bachelor, and later specialization was nuclear, subnuclear physics, particle physics. And my master and bachelor thesis, they were in theory. So this is like the very background I come from. Don't worry, I don't consider myself a theorist. So, but it was very useful for me to learn some basics of nuclear models, the QRPA methods, and so on. Later, I wanted to get more variety. So this is the point where I went for a Ph.D. degree. It was a double degree between Slovakia and France. So the Comenius University in Bratislava and Université de Bordeaux. This is exact point where I entered the collaboration which I'm in now. And here, this was more focused on experiment and the simulations. I also did a short postdoc in tritium project, which was in cooperation with Spain and Portugal. But afterwards, I got a postdoc at Czech Technical University, returning back into the SuperNEMO collaboration, and I started a group which is focused on simulations and data analysis. So basically, I try to be to put in my career experience from all kinds. So, but the most which I prefer to do is this latest tasks like simulation and data analysis. So the plan of the presentation is following. So first half is dedicated to introduction about some basics of double beta decay and our experiment. And the second half is about the activities we actually do, and it's split based on the system which this activity is related to. So let me start with a brief introduction of the problem. So you know this table, all of you, this is the standard model of the particle physics. And what we are the most interested in is this sector of neutral leptons, the neutrinos. There are a lot of things we already know about neutrinos. So for example, I would mention this, that we know that there are normally 3 flavors. Also very interesting observation came around year 2000, the existence of neutrino oscillation, which teaches us that the 3 neutrino masses, not all of them are 0. So this was something which basically made possible or made a motivation to search for what are these masses. So with the neutrino oscillations, unfortunately, we cannot say, we cannot measure these masses, but we know that they are not 0. And there are even more open questions, and I chose only few because I don't have time to talk about all of them. So interesting question is neutrino of Majorana nature or Dirac, which would mean that Majorana would mean that it's its own antiparticle. The problem of absolute neutrino masses, which I mentioned, so this is still open. We don't know what are they. We just know that at least 2 of them should not be 0. And also, we don't know what is the ordering of the masses, whether it's like 1, 2, 3 or 3, 1, 2, for example. So this is called the problem of normal and inverted ordering. And there are also many more questions which are being studied. but this is just to give you a glimpse. So now let's talk about double beta decay. So double beta decay is, if I would try to explain it simply, it's like two beta decays at the same time. So you have, instead of one electron, you have two electrons and two antineutrinos. And this was already observed, so there's no fundamental problem because it's also allowed in the standard model. And what is very interesting about this mode of decay is that the nuclei with which we observe it are basically considered as stable. I mean, for all the practical purposes, they are stable, but this is because the half-lives, I have them expressed here. In dependence on isotopes, they can reach 10 to 18 to 10 to 23 years, for example. So in something more tangible, you can say that it's hundreds of millions of age of universes and more. so it's really, really super rare, and it's difficult to search for it, but we found it. The hunt for double beta decay, when people mention it, it usually means that they search for this neutrinoless double beta decay. So it's a mode which would violate the lepton number because you don't have the two antineutrinos in the final state, and basically we have not observed it yet. So, but it would have some consequences which I will talk about. And if you don't observe anything, you also know it from the dark matter, you can still put some kind of limit. So in our case, it's a limit for the half-life, the lower limit. So I put this 10 to 26, but this is a bit misleading because it depends on the isotope. This limit, I think it's current limit for maybe selenium, I would say, to be checked, but this is roughly where we are at state of the art. So the double beta decay is energetically possible for several tens of isotopes. You can see some of them. So I chose the isotopes which are mostly used, but there are also some other ones which are more difficult to work with. They were studied, but this is like, let's say, the list of most studied. And usually the problem is, for example, enrichment, because you normally need to enrich these isotopes to reach enough of the nuclei which you want to have from the natural composition of the element. When I mentioned that double beta decay, the two neutrino mode, is like two beta decays, there is important disclaimer which I need to point out on this scheme. So if we take this system of the three nuclei, germanium 76, arsenic 76, and selenium 76, I want to stress that we do not talk about here two beta decays in a coincidence. And the reason is simple, that the germanium 76 in our example would like to beta decay to arsenic 76, but it's not energetically accessible. But selenium 76 is accessible. So these are the ways how we make sure that we just don't see two beta decays in a coincidence. And what is the importance of neutrinoless double beta decay? So there are two key points. So one is that the inverse half-life, if we measure it, we can directly relate it to the square of so-called effective neutrino mass. It's some kind of linear combination of the three masses. And the second reason is that this is currently the only way how we could prove that the neutrino is of Majorana nature. Unfortunately, it does not work the opposite way. So if we don't observe it, we still don't know. There can be non-existence of zero nu and neutrinos still be Majorana. Unfortunately, that's possible. But if we observe zero nu, we know that it should be Majorana. So these are probably the two main points why people search for neutrinos double beta decay. And in this presentation, I will show you only two equations, relatively simple ones, so don't worry. And this first one I particularly like because I like to show how all these parts of physics, particle physics society need to get together to reach the goal. So what you see is the equation from the previous slide. This is, of course, the effective neutrino mass. This is what we want to observe. This is the half-life. So this is what the experimentalists need to get to. And it's a rare event search. It's very difficult. You have to be underground and similar problems as you face with a dark matter search, for example. Then you have this phase space factor. This is a number which theoreticians need to calculate, but usually it's not a problem. It's usually well known. But there is another one which is called nuclear matrix element, and this nuclear matrix element it's based on the nuclear calculations, nuclear structure calculations. And you can see in this plot here. So this is a bit old table, but it pretty much shows the situation now. So if we look at this nuclear matrix element, it should be some kind of value. And if you look at any of these isotopes, you can see that based on different models, the value can differ even by a factor of 2, 3, 4, and it used to be even order of magnitude. So it's very difficult to calculate this, but this is also one of the factors which relate half-life to the effective neutrino mass. And even worse, it's to the power of 2. So this makes it more difficult to claim what is the mass limit when we measure some kind of half-life limit. So this equation I like because it shows how both the experimentalists and also the theoreticians, they have to put their best together if we want to reach the measurement of neutrinos double beta decay. So, and the second equation, and that will be it for the equations. It's about the challenge in the experiment, what we need. So on the left, you see something what we call half-life sensitivity. So that's the value which we should be able to measure neutrinos double beta decay if it exists. So this is the value which our detector should be sensitive to. We have here some constants which are more or less independent of the experimental design. So you can recognize Avogadro's constant, logarithm. There is also a number of sigmas. So that's like a confidence level which you want to reach. You can decide. But yeah, you want to compare with other experiments. And W stands for the molar mass of the isotope. So these things, once you set up the isotope, you cannot really move these values. What you can work with is the detector efficiency. So this is typically value between 0 and 1. You normally do not detect everything. That's a normal thing in physics. And the question is how much you are missing or how much of the real signal you actually can catch. Then I mentioned the question of need to enrich the isotopes, because natural abundance is usually 40% or less. If it's 40%, then it's great, but it can be something like 8% or so. So this value A tells what is the percentage of the isotope we want to see in the mixture in our source. Then more mass, more atoms, more nuclei, more time, more chance to atoms to decay. The energy resolution, I will talk about it in the next slide. And finally, this is also something which is very much related to dark matter. You need as few backgrounds as possible.
Yeah,
yes.
Ask a question. So why the source mass is within inside of a square root, and then this isotopic abundance is outside? This should be the same.
Okay, this is something which I need to cross-check whether A belongs under or because I think it has a reason. Like one thing.
You get my point, no?
Sorry.
It should be if just the number of or mass of this specific isotope should be. I thought the scale with this source mass, no? That's what my.
Yeah, I'm not sure. Like I did this calculation a while ago. We can discuss it later because there is also like you divide it by because mass because the background also scales as mass, but more like a square root. And now I think it's right, but yeah, I can cross check if needed. Yeah. So we need to also have the very low or background LED rate as low as possible, of course. And these are some tentative expected background levels. So Legend 1000, that's an experiment which should be running in 2030s, let's say. So the expected goal is something like 10 to the -5. And us with SuperNEMO, which we are actually going to run next week, we should be able to reach 10 to the -4. So let's hope. So that's just roughly the values where we are at. We of course talk about the background rate in region of interest. So and I still owe you discussion about the significance of energy resolution. So you can see that in a 2 neutrino mode, the neutrinos, they take away part of the energy of the decay. And the typical observable for a double beta decay is the sum of the two kinetic energies of the electrons. So naturally, if you look at this spectrum, you have the continuous spectrum for the 2 neutrino mode. For the neutrinoless, as there are no neutrinos escaping, all the energy goes into the electrons. So in the theoretical spectrum, you expect a delta peak at the end. So this is why we are able to do search for zero nu at all, because normally all the nuclei which are candidates for neutrinoless mode are also decaying by 2 nu mode. So the 2 nu mode is not possible to get rid of, because then you would get rid of your source, of course. So there is this minor problem. That left picture is of course theoretical one. If you apply the energy resolution, then you get something like on the right side, and then depending on how large this energy resolution is, you can have more or less overlap with the 2 neutrino mode. So that's the reason why also we care about the energy resolution. So, and how do we search for these? As I do not represent these experiments, I'm not going to talk that much about them. But for example, Kamlanzen is one of the leaders in the field. So you have a lot of approaches, really a lot. The people are trying all kinds of things. You can see some fluid and gas embedded sources. You have also a crystal project, some bolometric projects. And all this, or the majority of the field, is focusing on a methodology of homogeneous detectors. So the detector itself is also the source of the decays. So in SuperNEMO, we take a different path. So we have a heterogeneous approach, which is separation of the source from the detection systems. And on top of it, we also add the tracking. So we have a nice background rejection in the post-processing in the stage of the data. So this brings me quite naturally to the SuperNEMO experiment itself. So what you can see is the depiction, the scheme of the experiment. So in the middle, we have the source in the form of foil. It's roughly 200 micrometer thick. We use selenium-82, which has a nice Q value of around 3 MeV. This is sandwiched by the tracking detectors. It's several thousands of drift cells in Geiger mode. This helps us to reconstruct the tracks of the electrons. And finally, in the outermost layer, we have the segmented calorimeter based on the plastic scintillators. So these are the three basic systems we use. There are of course more, but this is the core of the whole experiment. And if you look at the cartoon depiction on bottom left, you can see a very simplified depiction of how our data look like. So you can see that there are the red squares, which is the energy measurement. You can see the individual electrons, their impact on the calorimeters, and the circles, they represent the signal from tracker, which I will talk a bit about later. And if you have a proper analysis tools, so the software, then you can reconstruct the tracks, you can reconstruct the vertex, and this is our trademark, our flagship in the field, that we have access not only to the sum of these energies, but we can also measure the single electron energy spectra and also the decay angles. So theoreticians are very happy about this. So it's a very specific bit standing out, but it's also not easy. So what you can see is some older pictures when the assembly was still going on. So on the left, it's the calorimeter wall. On the right, you see the picture of the selenium-82 foil. So it's split in, if I remember right, 34 segments. And here you can see also the picture of the tracker. The wires, there are thousands of them on the left, but you cannot really see it due to the resolution of the picture. And the status currently is that everything is assembled. The shielding is at place, and this week I got email that on Monday we should start taking data. So it's a big day. And the last thing I owe you is to mention where it is. So this is mostly French experiment, but we have also a cooperation with, there is a big part of the collaboration in UK, in Czech Republic, in Slovakia. And it's placed in French Alps in an underground laboratory in Modan. And this is the deepest laboratory in Europe. So we have a quite good muon suppression factor, like only 1 in million makes it down there. So yeah, this place is nice. And if this is older picture, you can see that SuperNEMO is not very photogenic because we had this cube there around. So that was the clean tent when we were building it. But when you take the whole laboratory, it's by far the biggest experiment there. So that's for the introduction of the two topics. And now in the second half of this talk, I would like to talk a bit about our activities, which we do with my group at CTU. This is definitely not the full list. I just chose the ones which look nice in the presentation. So first of all, I will start with the calorimetry and energy calibration system. So in the previous schemes which I showed, I had only the two walls. In those schemes, this is not the full picture because we have the calorimeters all around the 6 sides of the detector. So those two walls which you've seen in the previous scheme, we call them main wall, and then on top and bottom we call them veto, and then the short sides they are called X walls. The main wall, which is the main tool for measurement of the energy, we have the best calorimeters there. It's composed of 440 so-called optical modules, which is basically a polystyrene scintillator coupled with a photomultiplier tube. It's a 8-inch Hamamatsu PMT. The scintillator itself, this was a big success of Czech science, because those were all produced and delivered from Czech Republic. There is a small city north from Prague, and my colleagues, even before I entered the CTU, they worked on improvement on optimization of these wavelength shifters in the polystyrene with help of this company. So they improved a tiny bit the resolution. And you can see also my picture. This is from Bordeaux. I took part in assembly of the optical module. So this was the first one I finished. Then I also was involved in several projects concerning the energy calibration. So let me talk about one of them. But before I do that, I would like to discuss the calibration system itself. So we use bismuth 207 for the energy calibration. It's placed between the foils. There are gaps between the foils, 6 of them. So in this left picture, the circles, they represent the stepper motors, which can introduce and remove the red rectangles, which represent each single bismuth source. So we can very precisely place them at given positions. There are 42 of them altogether. And the choice of bismuth 207 was relatively clear why we did that. If you look at the scheme, so the reason is that they produced monoenergetic electrons. And the values of energy, 976 kV and 482 kV, it's the leading lines. There are many more, but these two leading lines are very convenient for our energy range. So this is what we use. And on the top right, you can see a picture of one of these sources. And yeah, that's my picture. So what I was working on is, if you take a look at the source, so the way how it was produced is that the droplet of bismuth 207 in liquid state was deposited on the foil and closed by another foil. So where the green spot is, this is how you would hope that the droplet is deposited between the foils. But what was a worry, these sources, they were used in the predecessor experiment called NEMO 3. And there was one worry that in the production process, the source might have leaked between the two copper frames. And if it would happen, then what we would see is that the electrons would be losing some energy in the copper, and this could decrease the quality of the calibration. So I got one task to find out what's the distribution. So I used one technology which we are very proud of at the Czech Technical University. It's this pixel detector technology. So the experts which we have, it's like literally half of the institute. They taught me how to operate it, how to calibrate it, and so on. And I went to Modern. I think it was something like 49 sources, and I tested them one by one. So I wrote some analysis analysis algorithms and created these kind of pictures. So it was quite difficult to get the red frame. So that's the topic by itself. But in principle, from this kind of pictures, I was able to fit the center and also roughly the shape. I approximated it with a circle. And you can also read more about it in the article which I published on this topic. And thanks to this measurement, I was able to do on the left this distribution of the centers and also some rough estimation what is the size of the droplet. So out of 49 measured sources, I rejected 5 of them, and then we had 44. And out of these 44, 42 were installed. So I was the person behind the choice of which sources should be eligible. Except for that, I also did activity measurement. That's also another topic, but I don't have time to talk about this. So over my PhD, one of the things, like the experimental part, which I really got experience in, was the measurements and the energy calibrations. And later, when I came to Prague, I had a bachelor and later master student, Filip. So with him, we worked on more software-related topic, which was the development of the calibration script. So this task is interesting because each of these optical modules, it works separately. So it's its own detector which has to be separately calibrated. So Philip's task was to develop calibration software which would be able to make the fits, then also control the quality of the fit if possible without the human intervention, and also taking into account several corrections. So there are some effects in the optical module, and those corrections, they were developed in Bordeaux by some PhD students. And what Philip worked on, except for the software, was to try to find a correction for the energy losses along the path of the electron. So you can see some typical calibration event. So the electron goes through the tracker and the tracker is full of gas. So we were wondering if we can find some nice model which would help us to compensate the energy losses. So he did so, and this is a result which, of course, it comes from the simulations because you could not really test it in real life. But this is the distribution of the energies of the electron from bismuth 207 from before the correction, without the correction, and the real values, the theoretical values, they are marked red. And when he applied his model, unfortunately, I don't have time to talk about it now, but when he applied his model, it's applied to each individual electron based on the track length. This is a big advantage of having tracker. He was able to put it almost where it should be. And yeah, we also did a few trips to Modan. He was helping, for example, with a cable plugging, as you can see. So we had a quite rich program in towards the calorimeters and also the energy calibration, and we still have. Another topic which we work on is the tracker itself, and we have a very responsible task in our team to work on. So what's the time? Okay, so what you can see here, this is the top view of SuperNEMO, and just so you better understand what's where. So in the middle, the horizontal plane, that's the source foil. You have the calorimeters, so the top and bottom lines, those are the main walls. And in the middle, you have the tracker. So the circles, they represent each Geiger cell, which works independently. And here is a cartoon representation of the cell. On the right, it's the view from top, and on the left, this is how it looks from side. The length is roughly 3 meters, so it's quite long. And the middle anode is under around 1.6 kilovolt tension. So when the electron is passing near the anode, it creates these avalanches, and the avalanche takes longer time to develop if the electron is further, and less time if it's closer. So if you have something what we call drift model, you can recalculate the distance. You can recalculate the time it takes for the avalanche to develop into the radius, like this. Of course, we don't know where from which side this distance was, from which side the electron passed, but you know what is the distance. And by following the signal which comes to top and bottom cathode, to both ends, by the time difference, you can also measure the Z value. So what you basically get is the anode wire position XY, the drift radius R, and the vertical position Z. So that's why data from each hit, from each cell, are represented by a circle hanging somewhere in the space. And this is the top projection, how, let's say, three tracker hits would look like. And the goal, the objective of the algorithm which I developed with another student is to find the track, to find the tangent to all of these tracker hits. So the crucial part of the reconstruction, not the full one, but that was the original idea, was to use the Legendre transform. Now it's only a part of the algorithm, and this is what I work on with Tomáš Křižák. So he started when he was a second-year bachelor, similarly to Philip, and now this June he will defend his master thesis. So before we get to some results, I would like to tell you a bit about the first stage of this algorithm, which is the Legendre transform. It's based on the ideas from these articles. So what you can see here is a representation of a semicircle. So the fact that it's a semicircle is just a technical thing. Do not get bothered by that. It's just due to some mathematical reasons. But if we assume this kind of semicircle, and if we decide to choose some point, let's say on top, you have always well-defined tangential line there. And this line has some parameters A and B, for example. So you can mark them in another plot, A and B plot on the right. And then what you can do, you can also decide to check another point which has its own unique tangential and its unique parameters. The same we can do for third one. And of course, I can be here for infinite amount of time, naming all the infinite amount of points, but I won't do that. I will just tell that if you do it for all the points of the semicircle, you can get this kind of line. And this is something what you call Legendre transform. And if we get another semicircle representing another hit, then you would get another Legendre transformation. So, and if you think about it, about the plot on the right side, it's all the tangential lines tangential to either one or another hit. But there is a sweet spot here, which is tangential to both of them. So in the world of mathematics, you already solved the problem. Okay. Of course, this is physics, so there is always some extra problem. But what you can see, this is a real event from a Bismuth 207 run. And this is how the data look like. Then you can make this, we call them sinograms, because don't get bothered that there is theta r instead of AB. It's just another representation of the line. And if you zoom in to the sinograms, you can find the solution. And then the solution gives you some parameters, and you can make fit like this. But this is the beginner level, okay? So what we learned at some point is that we have also more complicated tracks. So now what we do, we use the Legendre for clusterization. So it's a very good algorithm which can tell you which hits belong together. And I'm not talking about cluster which would represent particle, but the cluster which would represent one linear segment. Once you do that, we developed a model based on maximum likelihood method. And this helps you to do very precise segment reconstruction. But you see, we are not yet there because it looks a bit like random lines. And then what Tomáš developed, this is only a few months old, it's the construction of the whole trajectory. So there is processing which decides how this should be connected. And thanks to this, we can do quite precisely events like that. I think in the top part, there are maybe like 6 kinks or something like that. We call kink when you have this sudden change of direction. So we can do already something like this. So Tomáš did a really great job, and I'm pretty sure that he will defend his thesis in June. And he also wrote this kind of 3D visualization. So this visualization shows us or reminds us that this maximum likelihood method is not only for the top projection, but we wanted to introduce it to have a 3D picture. So it's really optimizing not in the top projection and the Z separately, but it's really optimization in the global sense. So, and this is the visual representation of that fact. So this is a quite interesting piece of work, and I also really like this project because it's creating a lot of nice pictures. And when you are building a house, you first build the base, the walls, and then you need the roof. So, and the roof, in our case, is the analysis. So I also have one PhD student who works on the roof, on the final analysis. I don't have that much time to talk about it, and especially when we are starting running with the real data, we will harvest the fruits only in months to go. But what I can tell you is that we have this nice idea which comes from our theoretical friends. They are real, but they do theory. So we search for exotic modes of 2 neutrino double beta decay. So this is possible thanks to our technology because, as I mentioned, we have access to the single electron energies, but also the angle between the 2 electrons. So this is a full topological reconstruction. And this also helps us to clean the region of the 2 neutrino mode of the background, and also do some kind of science, some kind of search for some theoretical predictions which no one could have searched before. Of course, we don't know the results yet because we will only take data, but we have some simulations. So, for example, what I mean is, if you look at the plot on the left, this is an angular distribution. In brown is the standard 2 neutrino double beta decay. So how the angles are distributed and how our detector would see it already with the detector effects. And there is theoretical possibility that there is a 2 neutrino mode where one of the neutrinos is right-handed, because the standard is an expectation of 2 left-handed neutrinos. And this would have a stronger preference towards closed angles, so something like a blue curve. And we can study how sensitive our detector is towards this. But you cannot do this study if you are not sensitive to the angle or to the topology, because the energy distributions, whether it's a sun energy distribution or single electron energy distributions, they are not so much different between the two options. So this is something we can do. Of course, we can also try to work with the multivariate spectra, so multidimensional analysis. So, for example, this is distribution of single electron energies on the left, or you can plot, for example, angle versus sum of the energies, and you can get, hopefully, it's a running research, hopefully we can get also better background rejection. And finally, what you can see here, this is something what Maros produced maybe a month ago. It's our first, let's say, more complex background model. And he made it with the great help of our colleagues from University of Edinburgh. So if you look at the region of interest of neutrinoless double beta decay, so around 3000 kiloelectron volts, you see that the expected number of counts during the whole run of the experiment can be something like 10 to minus 2 per 1 beam, which is something like 100 keV. So, and also it's a bit difficult to see with this logarithmic scale, but also before the 2 neutrino volt is basically dominant. So I guess it's very interesting how much we can achieve if we have access to all this information. But I have to say it's the more difficult path. it's you have to make all these systems, extra systems which others don't have. And so this was Maros, and my talk would probably not be complete if I did not mention maybe my favorite cooperation. And I have this cooperation with the Czech Technical University in Kyiv. So we started cooperation on the level of students where I offer them these remote internships. This is possible to do if you do data analysis and simulations. And so we worked with, for example, with Vladislav, we worked on some study of the distributions of the vertices from the bismuth sources. So what you can see on this plot is the data from a real detector when we just took data from bismuth 207, and we were trying to find the best criteria to see those points as clearly as possible. This is a great study also for the calibration of the geometry, of the tracker, and so on. So we do some quality assessment of the tracking. We also did, with Christina, we did some kind of fitting of OM waveforms. And also, yeah, I was able to come in May 23 to visit them, their group. So I really like this cooperation, and it's also very fruitful for both sides. So this brings me to the conclusions. I hope you are all well. So I just have few takeaway messages. If you don't remember anything else, but these are the main points maybe. So the neutrino physics is one of the fastest growing fields of physics currently. The neutrino is double beta decay. If it exists, it can provide the values of neutrino masses. And also it's currently the only way how we can really say, okay, neutrino is of Majorana nature. So it means its own antiparticle. SuperNEMO is maybe not at the forefront of all the detector systems, but it's definitely unique, and we have access to a lot of interesting physics with it. And we have also a lot of contribution to different systems, mainly in the field of simulations and future data analysis. So I would like to thank you for your attention. If you have some questions, you can send to email or even ask right now. I will be happy to respond. So thank you.